Hey guys, Miss Gosling here. In this video, we are going to discuss brightness and luminosity. By the end of the video, you'll be able to differentiate between and solve problems involving brightness and luminosity. So your two new vocab words of the day, brightness and luminosity. So let's go ahead and get started. So let's take a moment to differentiate between luminosity and brightness. So when we talk about luminosity, I am talking about the power that is radiated by a star in all directions, and this is what the star emits. So I'm going to measure luminosity in watts because luminosity is the power, is just the total power radiated. When I'm talking about brightness, on the other hand, I am looking at the power received per square meter. So brightness is not what the star is emitting, it's what you are perceiving. So brightness is how bright the star looks in the night sky, not how bright the star, not how strong the star is, not how much energy the star is producing per second. So when I'm talking about brightness, what I am talking about is I am talking about the watts per meter squared at a given distance from the star. And one thing that's really key to know, the farther I am from the star, the less bright the star will appear. In other words, as the distance between the star and the observer increases, the brightness decreases. So let's take a look at the two examples I have below. So I'm going to say for both of these examples, the power that is emitted by the yellow star is equal to the power emitted by the blue star. So what I want you to do, take a moment and pause the video. For the example on the left, I want you to tell me which star is more luminous and which star is more bright. It may be that they have the same luminosity or the same brightness. I want you to take a moment to pause, think about it, and then come back and see if you're right. Okay, so let's take a look. So luminosity is the power radiated by the star. So if the power is the same for the two stars, that means that the luminosity is also the same. So the luminosity of the yellow star is equal to the luminosity of the blue star. These stars are also both equidistant from me. So the distance from the observer to the yellow star is equal to the distance from the observer to the blue star. So because D yellow equals D blue, therefore, so since DL equals D blue and L yellow equals L blue, so my luminosity is the same and my distance is the same, then the brightnesses between the two stars must also be the same. So hopefully you said that the brightness was the same and the luminosity was the same. Now, if you were asked an IB question to tell me, to show or to explain whether the luminosity was the same or whether the brightness was the same, for brightness, you would be expected to give this explanation. So next, looking at the second example, again, pause the video and see if you can tell me, what is the relationship between the luminosity of my two stars? What is the relationship between the brightness of the two stars? So I'm looking for less than signs, greater than signs, equal to signs. Take a moment and pause and see if you can do this yourself. Okay, so in this case, my stars still are producing the same power. They are still emitting the same amount of energy per second. So that means that their luminosity is still the same. So the luminosity of my yellow star is still equal to the luminosity of my blue star. But now, the distance from my yellow star to my observer is a lot smaller than the distance from my blue star to my observer. So, since yellow star and blue star have the same luminosity, and the distance to my yellow star is less than the distance to my blue star, then the brightness of my yellow star is going to appear brighter than the brightness of my blue star. And the reason for that, let's think about it, right? So the sun is my yellow star. And let's say Proxima Centauri, the next closest star, is my blue star. Because the sun is a lot closer, the sun is a lot brighter in the sky. So hopefully these are the same answers that you got. So let's go ahead and start by formalizing our equation for luminosity. So luminosity, L, is measured in watts, and it's going to equal sigma, which is the Stefan Boltzmann constant, 5.67 times 10 to the negative 8th, times the surface area of my object times the temperature of my object. Now, in this case, we're looking at stars. We assume a star is a sphere. And so it's important to remember that surface area of a sphere is 4 pi r squared, because often you'll be given the radius of a star, not the surface area, and you'll have to be able to pretty comfortably translate from radius to surface area. Okay guys, so I'd like to go ahead and go through an IB example question. This one's a little bit of a tricky one, so please make sure you are very focused while you're watching. So before I actually get too into this example, what I'd like to do is I want to introduce you to a new symbol that you're going to see. It looks like this. And this simply means the sun, as it is today. So we can use it, for example, to signify the radius of the sun, or the mass of the sun, or the luminosity of the sun, or the temperature of the sun. So I just want to make sure you're used to that because you're going to see a lot in questions this unit. So without further ado, let's get into this specific question. During its evolution, the sun is likely to become a red giant of surface temperature 3,000 Kelvin and luminosity 10 to the 4th times the luminosity of the sun as it is today. Later, it is likely to be a white dwarf of surface temperature 10,000 Kelvin and luminosity 10 to the negative 4th times the current luminosity of the sun. We need to calculate the radius of the sun as a white dwarf, so that's R white dwarf divided by its radius as a red giant, which I'm going to call R times radius as a red giant. So what I'm going to do first is I'm going to take my equation for luminosity, L equals sigma A T to the 4th, and the reason I'm doing this is I'm given luminosity and temperature, and I want to find radius. So this equation has luminosity, temperature, and surface area, which we of course can replace with an equation, a function of radius. So as we know, surface area is 4 pi r squared. So instead of area, I'll write 4 pi r squared and t to the 4th. And since I'm looking for a ratio between two different radii, I of course need to start by solving this equation for radius. When I do, I get that radius is equal to the square root of luminosity divided by 4 pi times sigma times t to the 4th. And what I'm going to do is I'm going to go ahead and now write the ratio for the radius of the sun as a white dwarf divided by its radius as a red giant. So since both of these are going to be under square root signs, I can just write one big square root sign for both. So luminosity as a white dwarf divided by 4 pi times sigma times my temperature as a white dwarf to the 4th. And that's all going to be over my radius as a red giant, which is my luminosity as a red giant divided by 4 pi times sigma times my temperature as a red giant to the 4th power. So to simplify this, I'm going to go ahead and take my bottom fraction and move it to the top, like so. So we're going to flip our bottom fraction and multiply the reciprocals. When I do this, I get that the ratio of my two radii is equal to my luminosity as a white dwarf times 4 pi times sigma times the temperature as a red giant to the 4th, divided by 4 pi times sigma times my temperature as a white dwarf to the 4th times my luminosity as a red giant. And so now we're at my favorite step, which is just canceling everything that shows up in both. So 4 pi and sigma can go away. and I get that the ratio between my two radii is my luminosity as a white dwarf times my temperature as a red giant to the fourth, divided by my luminosity as a red giant times my temperature as a white dwarf to the fourth, square root. And now I'm ready to plug in numbers. So my luminosity as a white dwarf is 10 to the negative fourth times the luminosity of the sun, and my temperature as a red giant is 3,000. And we're going to raise that to the fourth. My luminosity as a red giant is 10 to the fourth times the luminosity of the sun, and my temperature as a white dwarf is 10,000 Kelvin, which again gets raised to the fourth power, and we're going to take the square root of that whole thing. I can also cancel out the luminosity of the sun since it appears on both sides of my equal sign. And now at this point, all I need to do is plug everything into a calculator. When I do, I get that the ratio of my radii is 9 times 10 to the negative sixth. Okay, so we've talked luminosity. Let's go ahead and move on to brightness. So brightness, again, aka apparent brightness, is how much light I am receiving from here on Earth, or from wherever I'm measuring wherever I am measuring brightness. So brightness is equal to luminosity divided by 4 pi times the distance from me to the object squared. So that's all pretty straightforward. So let's go ahead and look at a new IB example question. The data for the star Eta Aquilae A are given in the table. Here. Estimate in parsecs the distance to Eta Aquilae A using the luminosity in the table, given that the luminosity of the sun is 3.83 times 10 to the 26th watts. So the first thing we need to do is figure out the distance to Eta Aquilae A. So we know that brightness is equal to luminosity divided by 4 pi times distance squared. And the reason I know to use this equation is this is asking me for distance, and it's giving me luminosity, and I know that the equation that relates luminosity and distance is my equation for brightness. So what I'm going to do first is I'm going to get distance by itself. And when I do that, I get that distance is equal to luminosity divided by 4 pi times brightness, and the square root of that whole fun thing. Plugging in my numbers, I get that my distance, and again, this is my distance in meters, is the square root of luminosity, which is given in the table as 2630 times the luminosity of the sun, and the luminosity of the sun is given here as 3.83 times 10 to the 26th watts. And that's divided by 4 pi times my apparent brightness, which is 7.20 times 10 to the negative 10th. And I'm going to go ahead and just throw those numbers in a calculator. After putting everything in a calculator, I get that the distance from me to Eta Aquilae A is 1.06 times 10 to the 19th meters. Now, I am not done yet because I am asked to find in parsecs what that distance is. So what I am going to go ahead and have you all do, I want you to pause the video, and I want you to see if you can calculate the distance from me to Eta Aquilae A in parsecs. So see if you can do that unit conversion on your own. Okay, so let's go ahead and see how to do it. So I know that my distance is 1.06 times 10 to the 19th meters. I want to convert from meters to parsecs. And I know that 1 parsec is 3.09 times 10 to the 16th meters. So 1 parsec is 3.09 times 10 to the 16th, so I'm going to make sure I put the numbers where they go. I'm going to divide my answer by 3.09 times 10 to the 16th. And what I get is that my distance is 341 parsecs. There you go. So hopefully you all got the same answer when you tried this on your own. So what I'd like you to do is take a moment. I want you to write this question in your notes, and I want you to take a moment to jot down an answer. Why is knowing both brightness and luminosity useful? Okay, so here are a few reasons why knowing both brightness and luminosity is useful. So first, if we know both brightness and luminosity, we can figure out the distance of a star. So knowing brightness and luminosity is useful because it helps us find distance. The trick here is that it's not always, we don't automatically just magically know the luminosity of different stars. Instead, we need to pay attention. We use some special kinds of stars, which we haven't learned about. We're going to talk about them throughout the course of this unit. But some of the special stars have a defined luminosity, so they have a luminosity that we know. As a result, it's easy to figure out the distance from Earth, and because these stars have standardized luminosity, we call them standard candles. And again, we haven't learned about what stars they are yet, but we will. And you'll be able to understand why luminosity and brightness are so useful for building a detailed map of our night sky. So let's talk about takeaways. First of all, luminosity is the power radiated by a star, while brightness is the power received per square meter at a given distance from the star. Finally, and most importantly, if we know both luminosity and brightness, we can determine distance. And it's easiest to do this for stars we classify as standard candles. So with that, go ahead and try solving some of these luminosity and brightness questions on your own. Best of luck and happy solving.